先跟大家说声不好意思哦，因为助教不知道说这个整个那个就是呃流程哦，所以说呃造成了一些误解哦。理论上应该是助教先 host 这个 meeting，直接是有一些同学可能在线上等了一段时间哦，但是这个不应该发生。可能助教呃前面学长没有跟他讲说怎么样做，好吧？Anyway，那大家可以听到我讲话吗？对，可以听到哦。OK，好，好，那我们就开始哦。等我一下，哦，这个 OK，so okay, let's continue our discussion. Last time, we only had time to talk about the first example on this slide. Okay, uh, the next one. Okay, to show that 1x, x squared, x cubed are linearly independent in P3. This is very easy. Okay, basically just like a times one plus b times x plus c times x squared plus d times x cubed equal to zero. Okay, so this is like the formula. Okay, well, I mean, according to a linearly independent, uh, you know, uh, uh, you know, uh, definition. Okay, so in order for this formula, okay, to hold, okay, we need to show A, B, C, D are
教
all zero.
授，不好意思打扰，我是毛茂生，然后现在好像没有分享到画面。
啊，等一下，现在有画面了吗？
有了。
奇奇怪，刚刚明明是有的啊怎么变成全荧幕就被跑掉了？OK，好，对，我们上次讲过第一个那个例子嘛，那第二个这个例子，OK，so I mean we will begin from here，OK，so um so to show that one x squared x cube are linearly independent, okay, in P3, okay, the important thing is like the definition of linear independence. So, to show these are linearly independent, okay, we just, A times 1 plus B times X plus C times X squared plus D times X cubed equal to 0. We need to show that, you know, for this equation, this formula to hold, A, B, C, and D they have to be all zero. Okay, because here, okay, I mean, keep in mind that this X is uh you know any it could be any number, right? It could be any number. So in order for this equation to hold, basically, you know, uh, this A, B, C, D must be all zero. Okay, why? Okay, well, you can think about this like, you know, that I just say like a plus bx plus cx squared plus d cube equal to 0, right? So you just consider when x is 0, okay, then all the terms with x will will vanish, right? So the only term you left is like a on the left side, and the on the right side is 0, right? So you get a must be 0, okay? And then once you have a to be 0, okay, then the first term is gone. So it becomes like bx plus cx squared plus d cube equal to 0, right? Then, again, I mean, you can assume, you can try to use like any value that, you know, basically make sure apply like similar technique. Okay, just plug in like some numbers. Okay, and you can solve this like B, C, and D to be all 0. Okay, so this is relatively easy. Okay, according to a linear dependence definition. So we are done with the section 3. Okay, so before we continue, okay, to for the section 4, okay, basis and the dimension, okay, few things I would like to two things I would like to share. Okay, the first thing is that, okay, as I mentioned last time, okay, because of the consideration of the long weekend, so we will. I mean, today we do this lecture online, and oh, shoot, there are some other student waiting. 所以茂轩，我就跟你讲说，你晚上也是你 host 的吗？
是，
那你要记得，你要先登录，用我的账号登录，
好好
这样子，如果说学生在等，你就直接可以把它弄进来，然后我在上课的时候，你也可以直接把它弄进来。对
好，
对对
我研究一下。
对，你可以问一下学长啦，就是说学长他们都有做过类似的事情啊，你可以问他们啊。
好，
对对对对对，我说怎么会发生这种事？
不好意
好，
思。
哎，anyway，呃，这个the first thing，okay，呃，in the online lecture, okay, I think like it's uh, probably a better idea that we do the break in only two times. In other words, like we will have a break in the middle of the lecture for about 20 minutes. Okay, and then we will finish the lecture around 11:50. Okay, the third break, I mean, will remains the same, but the first and the second break, I mean, will be combined. Okay, I think this is like more convenient because like having like short breaks, too many short breaks, I mean, it doesn't help like the progress of the lecture. Okay, especially like for the online class. Okay, so you know，就是说我们中间那个下课哦，就是不需要这样子每一小堂课就下课哦，我们就那个第一堂跟第二堂的中间的下课，我们就把它 combine 起来，就是中间下课20分钟，然后最后面结束的时候还是11:50啊，就是大概是这样的情形。对，先跟大家讲一下哦，就是这个，因为线上课程太多的这个中间的下课，其实比那个实体上课更不容易那个就是怎么讲，就是回来哦，就是所以我觉得说这样子安排可能会好一些。OK OK so this is the first thing. OK the second thing. OK is that OK I told you guys that we will have the third quiz like next week. Sorry, the week after next, right? Which is what's the date? I'm sorry. Let me check my calendar. So it's going to be 15th, right? 15th. Okay. Um, so uh, the the quiz three will be given at the beginning of the lecture. Okay, at the beginning of the lecture. Okay. So please, I mean, keep in mind. Okay, this is like also just the situation is kind of like um, the last quiz I gave. I mean, because it's kind of like a delayed one. So I will, just uh, you know, hold a quiz at the beginning of the lecture. Okay. Um, so please make sure, okay, to come to the lecture on time. Oops. Okay. And oh, one more thing to mention. Okay. So we will have the um, uh, oops. we'll have the midterm. Okay. A week after the third quiz. You know that, right? Okay, which is let me see, 22nd, October 22nd. Okay, so this is going to be the midterm, okay, for our class. Okay, October 22nd. Um, the practice midterm should already be posted on the EE class. Okay, please check it out. Okay, the problem will not be the same, but I will make sure the format like is similar. Okay. Okay. So back to the lecture. Okay. Oh, sorry. One last thing. Okay. Uh, the let me see. And I also mentioned that uh, the lecture on the 29th. Okay. Because I will not be like um Taiwan. Okay, I will be in Malaysia for a conference. So what we can do is that okay, we will hold the class like on the 25th. Okay, as usual, like before the weekend before the my trip. Okay, and it's going to be similar to today. Okay, um, I think like or you can do it. We could do it like a face to face. It's up to you. But that weekend is not supposed to be a long weekend. Okay, but 25号是台湾光复节，台湾光复节是放假吗？有人知道台湾光复节是放假吗？哎，有人要进来，
24号有补假，
啊，24、24号、25号也是放假，是不是？
对，
所以那25号那个也是 long weekend，是不是？天哪，好吧，那我们就维持像今天这个样子，好不好？long weekend 的话，叫大家回来上课好像有点残忍。对，我们就25号的那一次的，也是按照我们这样子来安排，就是那个线上，OK。那我还是会请助教提前把 meeting link 发给大家，然后那个就是25号，请大家记得礼拜六早上会有课，好不好？对。那不要那个影响大家的那个 long weekend，你们要去哪边就去哪边，只不过记得早上起来上个课，OK，好，OK，这个是最后的事情交代，OK，OK，go back to the lecture，OK，so basis and the dimension，OK，so first, okay, is the definition, okay. The vectors v1, v2 to vn, okay, these n vectors are said to be a basis, okay, for a vector space V if and only if v1 to vn are linearly independent and the v1 to vn span V. So these two, if these two condition holds, we say like this V1 to Vn are the basis for vector space V. Okay, or if vector space has a basis like no this V1 to Vn, they have these two properties. Okay, because this is if and only if, right? So we can verify some examples are basis very easily. For example, like E1, E2, E3. What are the E1, E2, E3? Okay, E1 is like 100, E2 is 010, and E3 is 001. These three column vectors, okay, obviously would be a a basis for R3, right? Because they are obviously independent, linearly independent, and any vector in R3, you can use the E1, E2, E3 to to spend it. Okay, so we say E1, E2, E3 are will be a standard basis. Okay, because obviously, like it's a relatively easy choice. Okay, um, and the similar extension can be can be extended to like a R2, R4, R5. I mean, basically like for example, R2 is just like a 1001. Okay, these two vectors are will be a standard basis for R2. Okay, for R4, I mean, you get the idea. Okay, so in addition, okay, so these two sets, okay, this 111, 011, 201, okay, and another set 121, 301, 2 negative 1, 1, okay, these two set of vectors are bases of R3. Okay, so how do we show that? Okay, in order to show, for example, this 111, 011, 201 is a basis. I mean, you have to show it satisfies above two requirements, right? First, you need to show these three vectors. They are linearly independent. Okay, in other words, like A plus the first column vector plus B plus the second column vector plus C plus the times the third column vector. Okay, they equal to 0. The only possible solution for ABC will be 0. Okay, uh, and we talk about this like basically you just verify if this if you try to consider these three column vector as like a matrix, you just check like if the determinant of this matrix is non-zero, right? If it's non, if determinant of this of the matrix formed by these three column vectors is non-zero, then we know like there's the solution ABC must all be 0. Okay, then we can show that these three vectors are linearly independent. Then we need to show these three vectors span V. Okay, so in other words, like we need to show like if we have a vector, for example, like say the vector in R3 is ABC. Okay, then alpha times 111 plus beta times 011 plus gamma times 201, okay, will be this ABC. So again, okay, you can sort of like consider this is like the matrix formed by this three column vector times our alpha, beta, gamma equal to ABC, right? Where ABC are arbitrary. In order to show that this is always, there's always solution for this thing. Okay, again, the important thing is whether or not this matrix has inverse, right? If it has inverse, like we multiply the inverse of this matrix on the left hand side on both sides, then we immediately get like alpha, beta, gamma. So again, to show that this matrix has inverse, you know, again, basically you need to show that determinant of this matrix is non-zero. Okay, so so as a result, okay, if the determinant of the matrix formed by these three column vectors is non-zero, then both of these conditions will be satisfied. Okay, in other words, like these three column vectors are form a basis for R3. Okay, the similar approach can be, done for the second example. Okay, yeah, I mean, the writing is not easy. Like, if it doesn't look good, like, please, what should I say? Like, um, yeah, I think like it's I mean, the in-person lecture, okay, uh, the best thing for in-person lecture is that we have a blackboard, okay, which we can do it like the writing easily. Uh, for online class, like uh, I if I have like一个平板电脑上面可以写字的那种，it might be easier for me to to conduct like a lecture because like a lot of time like I need to write something to show like how it works. But if I only got like a mouse and a keyboard, it's not that easy. Okay, but you get the idea. Okay, the important thing is to show like the determinant of the matrix formed by these three column vectors is non-zero. Same thing here. Okay, you need to show determinant of the matrix formed by these three column vectors is non-zero. If that's the case, first, these three vectors will be independent. Second, like you can use these three vectors to span any vectors in R3. Okay? Sorry. Okay. So another easy choice is like we say like uh uh no the R2 by 2. Okay, it's like the uh vector space formed by like a 2 by 2 matrices. Okay. The set E1, E11, E12, E21, E22 is a basis. Okay, where E11 is one, the upper left corner is one, the other are zero. E12 is like the upper right corner is one, all the other elements are zero, and so on. And the reason these four matrices form the basis for R2 by 2 is also trivial. It's just similar to what we why like those like the E1, E2, E3 is a standard basis of R3. Okay, it's a similar. The argument will be similar. Okay, and you could say like this E11, E12, E21, E22. Okay, this set of like a matrix to be like a standard basis for R2 by 2. If you want to say that, okay, it's similar. Okay, and the last one is kind of interesting because like we talk about null space, right? And we previously we show that null space is also vector space, right? So and if you still remember, we used this example, this matrix like okay, null space for this matrix is this one, right? And obviously, these two vectors spans all the vectors in the null space. Just look by the looking of the by looking of this definition of the sets. And the second, these two vectors are obviously linearly independent. Why? Just look at the last two elements. The last two elements, okay, it's a 1, 0. The last two elements of this second vector is 0, 1. In order to, if you have like a times the first vector plus b times the second vector equal to 0, in order for the third element and the fourth element to be 0, the A and the B has to be all 0, both 0. Okay, so in other words, like these two vectors are linearly independent as well. So, these two vectors is a basis of like a null space NA. Okay, so we finished like some examples of those like basis. Okay. Oh, and by the way, I forgot to mention. Okay. In for R3, obviously we talk about three different bases here, right? For R3, and you would be it. I mean, it's an interesting observation, that all these three bases have three vectors. The number of the vectors in each of these bases will be 3. Okay, so actually, this will be connected to the dimensionality. Okay, as we will talk about it later on. Okay, but for now, let's finish other stuff first. Okay, so here's the theorem. Okay, if V1 to Vn, okay, if this is a spanning set for a vector space V, then any collection of m vectors in V where m greater than n is linearly dependent. Okay. So if you have like a basis, okay, with n, not sorry, not the basis, like a spanning set. Uh, uh, if you have a spanning set of n vectors, okay, any vector, any vector, any set of vectors greater than n has to be dependent. Okay. So how do we show that? Basically, okay. Yeah, I mean, usually I would just write it on the blackboard, but obviously, like when I'm doing like online classes, it's a little bit difficult. So, I'll rely more on like a slide. Okay. So anyway, okay, let U1, U2 up to UM, okay, be those M vectors, okay, in V, where like this M, we have like more vectors, okay, than N here, okay? So eventually, we need to show that, okay, this N vector, U1, U2, blah, blah, UM, these M vectors are linearly dependent, right? We need to show that. Okay, but before we do that, okay, let's consider this. This U1, U2, blah, 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 UM, each of these UI is a vector in V, right? Because each of them is a vector in V, and we say previously, like this V1 to Vn, this n vectors span, it's a spanning set, right? So it means like this n vectors span V, right? Or put it another way, any vector in V can be written as the linear combination of these V1 to Vn vectors, right? We know that, right? So we can write U1 like a linear combination of V1 to Vn. U2 can be written as a linear combination of V1 to Vn, and so on. So we write it like this. Ui to be AI1 V1 plus AI2 V2 plus blah, 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 plus AIN Vn. Okay, so this is valid for U1, U2 up to UM, okay? Because each of these UI will be a vector in V, and this V1 to Vn spans any vector in V, okay? Then, okay, when we consider this is C1 U1 plus C2 U2 plus blah blah plus CM UM equal to 0. Okay, this because if we want to show U1 to UM are linearly dependent according to the definition, we need to show C1, C2, blah, blah, blah to Cm. Okay, they have non-trivial solution, right? Non-trivial solution means that they are not all zero. There's a possible assignment that they are not all zero, and this equation is valid, right? So now let's plug in this U1, and the U2 and so on using the above formula. Okay, so it becomes like this. Okay, and well, this is a little bit jumpy, okay, from this one to the following one. Because U1 is like a linear combination of like a V1, VIs. U2 is a linear combination of VIs, and so on. Vm is a linear combination of VI. So we can sort of like, so each of these has a V1, right? So we can, get the V1 from every term here and put it together here. And we get V2 from every term here to put a V2 here. And this is like the leading coefficient and so on. So we can, sort of like, reorganize them into this one. Okay. And if we write it, okay, a little bit, in a matrix form, in the form of a matrix, okay, this would be, because this is AI1 CI summation, AI2 CI summation, and so on. So this formula is equivalent to this matrix multiplication, right? If you try to multiply, for example, A11 times C1 plus A12 times C2, blah, 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 the first row times this one is 0. Okay, that means this one, right? This is 0. The second row times this one equal to 0. That's this one, and so on. So it just this matrix, okay, shape is just like we try to write the above formula. We just try to represent the above formula in the matrix form. Okay, and we want to see. Remember, like our purpose. Our purpose is to show like whether or not this CIs here exist non-trivial solution, right? So if we have a non-trivial solution for this, matrix, like a format, like a formula, then we pretty much show like these UIs are linearly dependent, right? But look at this matrix, because this matrix m greater than n, right? M greater than n. What is the meaning of m? M is number of columns. N is number of rows. You have more number of columns than the number of rows. Okay, I believe by now you guys have played enough like a Gaussian elimination to know like, if the matrix is of the shape like you have more columns than the number of rows, then obviously you will have non-trivial solution. Okay, here, because this is homogeneous system. Homogeneous system, you guarantee to have one solution. In other words, like C1 to Cm, to be 0. This is a guarantee to be like to have at least one solution. The issue is whether or not you have like additional solution. But since like you have more column than the row, so if you use like Gaussian elimination, what happens is that you will have like some free variables. Okay. Oh, sorry. 啊，又有学生要被加进来。So you have like some free variables. In other words, you can assign those free variables. Okay. When I say free variable, I mean like some of these CIs will be those free variables, and you can assign like those CI to be non-zero. Okay. So in other words, like this CI has non-trivial solution. Okay. So in other words, we know like this C1U1 plus C2U2 plus CMUM equal to 0 has non-trivial solution, and as a result, U1, U2 plus UM are linearly dependent. Okay, so we have proved this theorem. Okay. When I'm doing online class, I obviously cannot like check like a message right away. But if you have any question, you can write it in the you know 聊天室 message box, and I will try to check those message box like every couple of minutes to make sure like your question is addressed. Okay. I mean, if you want me to repeat a particular part, okay, that's fine too. Okay. So finally, we are in a position to talk about dimension. Okay. So from the above, we know the other set, like greater than n, are linearly dependent. So let's come back to the basis. I mean, basis, according to the second requirement, the basis is a spanning set, right? The basis is a spanning set because this basis, the vectors in this base in a base must span that vector space, right? Okay. So in other words, if we have two bases, okay, for the same vector space, then we can claim these two bases, they have the same number of vectors. Why? Okay. Without loss of generality, okay, let's assume like v1, v2 up to vn, okay, the n is smaller than m. N is smaller than n. Okay, so we have more number of vectors, okay, in the second set than the first one. Okay, but because both of them are bases, right? According to the definition of the basis, okay, first, v1 to vn would be the spanning set for v, right? And the second set, okay, this u1 to u1 to um, according to the definition of the basis, these vectors are independent, right? Remember, that's like here. For if you have a basis, okay, these vectors in this basis must be linearly independent, right? But then, okay, we have we have an issue. Why? Because in the previous theorem, we just show that, okay, if we have a spanning set, okay, with an n vector, and any set of vector greater than n cannot be linearly independent, right? We show that, I mean, this must be linearly dependent. In other words, it is not linearly independent. So we in other words, like, so if the first one is the basis, the second one cannot be the basis because they are linearly dependent, right? So the only possible explanation is that n, the m cannot be greater than m. M cannot be greater than n. Okay, and the vice versa. Okay, if you use the same argument, okay, u1 to um spans v, and you can easily show that v1 to v1 to vn, cannot be linearly independent if n greater than m. So if m greater than n is not possible, and n greater than m is not possible either, then the only possibility is n equal to m. Okay, and this also explains, remember, like previously when we talked about like the basis for like R3, okay, you will find that sorry, we talk about this, right? The E1, E2, E3, or this one, they all have like exactly 3 elements. Okay, so this explain this phenomena. Okay, then okay, because like any basis for a given vector space, okay, the number of vectors is the same. So we can define, okay, that as a dimension for this vector space. Okay, so let V be a vector space. If V has a basis consisting of n vectors, we say that V has dimension n. Okay, so I mean, previously, like or like in like physics, okay, or in any other places, like you probably have used the term dimension. OK，就是我们常常讲说我们在什么三维空间啊，whatever，尤其在学物理的时候，OK，三度空间啊什么，in mathematically speaking，OK，在数学上，this is the first time you learn the formal definition of dimension. Okay, I mean the previous description of the dimension is, what should I say, like mushy. OK， 就是不是很精确的。OK， 那so just want you to understand. OK， usually we define the dimension as the number of vectors in a basis. Okay, for vector space. Okay. Okay. So as a result, okay, let's consider some, for example, the subspace 0. We know like a 0, okay, like this 0 means like a 0 vector, okay. Keep in mind, like, the empty set is not subspace. We know that, right? Like any subspace must be non-empty. Okay, so this one just represent like a zero vector, just one vector, zero vector. So this is subspace, or you can say this is a special vector space. It's a vector space. Okay, and it's also a subspace of any vector space. The okay, it's said to have a dimension 0. Okay, this one because like it only has one vector, and there's no, if you consider like its basis, it does not have any vector in the basis, so the dimension is 0. So V is said to be finite dimensional if there is a finite set of vectors that spans V. Okay, otherwise V is infinite dimensional. Okay, so all the stuff that we discussed earlier, most of them, majority of them, are like finite dimensional. Okay, let's consider a few of them. Okay, obviously Rn is finite dimensional. Okay, you can consider like just like for Rn, just consider E1, E2, E3 up to En, right? The standard basis. Okay, then obviously it has n number of vectors in this basis. Okay, so Rn times n. So because you have m times a number of positions in the matrix, right? So each time you just put one in one position and all the other position to be 0. Okay, so take turn to do that. You have like m times n number of matrices that form a basis for this Rm times n vector space. So in other words, okay, this basis has m times n, well, you can say vectors or you can say matrix, whatever you want to say it, but basically the dimension of this vector space is m times n. Okay, and the Pn, what is Pn? Pn means like the polynomial. Okay, all the polynomial with degree up to n. So in our world, for example, P3, okay, it contains all the possible polynomial a plus bx plus cx squared plus d cube, right? dx cube. Okay, so Pn, okay, obviously 1 x squared, x cubed, x to the power of 4, blah 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 blah, and x to the power of n. Okay, this n plus 1 elements, not only they are linearly independent, but also they span any elements in Pn, right? So in other words, this set forms a basis for Pn. And you can say like Pn has a dimension n plus 1. Okay, and the only basis that we have discussed so far that is not finite is, the Cn minus 1 AB. We talked about this like, as an example previously, because this one contains like any function continuous, that is continuous over a range of A and B. And this n minus 1 means like, this function has to be continuous in the range of A and B. After n minus 1 differentiations, then, let me just, we know any polynomial must satisfy this requirement, right? So this pretty much is this vector. There are other functions, obviously, that satisfy this, but obviously, no, just consider all. I mean, all the possible polynomials. Then the dimension is infinite already, because the previous Pn, we bound a vector, the polynomial degree to be n, right? The polynomial degree is bounded by n. But here, okay, if you consider the polynomial, the polynomial can be n can be any number. Not to mention all the other possible functions out there. There are too many. Okay, so obviously, there are, if you try to find a basis that expand this, it's going to contain infinite number of vectors. Okay, so that's some examples for the dimension. So the next one, if V is a vector space of dimension n greater than 0, okay, in other words, it's not a zero vector only, okay, then any set of n linearly independent vector span V, or any n vectors that span V are linearly independent. Okay. Unfortunately, I don't have slide for that, but so let's try to prove that. Okay. The first one. Okay. Any set of n linear independent vectors span V. Okay. So we know the dimension, this vector space is dimension n already. Okay. So what should I don't know if I have enough space. Okay. So let's first talk about the given. Okay, the given stuff. Okay, because we know V is dimension n. So in other words, there exists a basis with n vectors. Okay, and these n vectors, they are linearly independent, and they span V, right? So this is a given. Okay, and then we want to say any set of unlinear independent vectors spans V. Okay, so where should I write? I don't have much space anywhere. Okay, say that these unlinear independent vectors are V1 to Vn. Okay. Oh, this is crazy. So we want to show, what we want to show is that, you know, uh, A1 plus A2 V2 8 plus plus ANVN, okay, equal to, you can span any vector. So this V, assume V is any vector in capital V, in the space V. Okay? So this is like the goal we want to achieve. Okay? Then, and assume like the vectors, the basis, the basis is U1, U2, okay? Da, da, da. U and notice that these they have the same number, okay? Are the basis. These are the basis for V, okay? So first, because this U1 to UN are the basis for V, then obviously uh, uh, U1 to UN span V, right? So we know like uh, we can write V as a linear combination of UIs, right? Uh, is there a way like one moment. Let me think of a better way. Okay. Otherwise, this writing is just not going anywhere. Let's take a break, okay? And I'll prepare something for this. Okay, otherwise it's not easy for me to explain. Okay, I'll have to find something that is already written. Okay, then I can explain easily. Okay, let's take well 20 minutes. So let's come back around like 10:27. Is that okay? Let me find like the stuff for you.